Hi, my name is Brad Ambrose, and I'm a professor of physics at Grand Valley State University. I'm a member of a team of physics and astronomy education researchers who are developing guided inquiry teaching materials for teaching physics concepts, but in astronomy and space science contexts. This is work that we are doing in support by NASA Goddard through a grant for which the co-PIs are Professor Ramon Lopez of the University of Texas at Arlington and Professor Janelle Bailey at Temple. And so this is a project that's done with Temple and AAPT as partners with NASA. And this particular presentation that you're watching, it's one of a series of presentations done in conjunction with workshops that we are doing to disseminate our materials. And the particular tutorial that I'll be talking about in this presentation is a guided inquiry tutorial on the physics of habitable zone planets. So I'll be starting with what we mean by this. What is the definition of habitable zone? And in so doing, what I'll talk about through this tutorial as I describe it, I'll talk about some of the data sets, both current and past projects from NASA, including the Kepler Space Telescope that we'll be using and have students interact with as they progress through the tutorial. And the basic ideas from physics, from introductory level physics, and also probably a sophomore level treatment of modern physics. Black body radiation will be a foundational idea that we build upon, including, or in addition to that, how intensity varies with distance from a source and other factors that play into what might be an approximation for finding an average temperature for a heavenly body like a planet. So, and that's what it's all about. When we're talking about the habitable zone of a host star, we're trying to find where a planet would have liquid water on its surface. So that means finding some sort of Goldilocks zone where the planet is not going to be too hot, not too cold. The graphic here shows nicely in the green regions where the habitable zone might be for stars of different temperatures. And so in trying to find not just as many exoplanets as possible, but where are exoplanets likely to be in habitable zones, what we can turn to is the Kepler Space Telescope project, which has identified many exoplanets of many sizes, of varying orbital periods. And the data set that we have students work with is a small slice of this. And it's actually shown in this graphic, where students will look at this plot, analyze this plot. We see on the horizontal axis, energy received by a planet, the vertical axis, the surface temperature of the host star. And as they work through the tutorial, students will recognize that the horizontal axis is really the intensity of the incoming solar radiation that's received by the planet. And interpreted in this way, and with the benefit of having Venus, Earth, and Mars, and our sun included on this plot, what students will be able to do is take data, for example, for this example exoplanet, the one that's indexed 7954.01. Students will be able to interpret this plot, and in so doing, recognize with the 1/r² relationship in mind, students will know a way to estimate how far this exoplanet must be from its star, assuming its host star is just like our sun. And so when students work through this tutorial, and what I'll be describing here is a process to approximate using what might be a pretty crude approximation at first, but using black body radiation as a way to start on this kind of an approximation. So we're going to assume for the beginning that planets can behave like black bodies, and black bodies are perfect absorbers of light, of radiation coming toward them. We also know that black bodies radiate energy at a rate related to their temperature. This capital R quantity, radiative intensity, that is the rate at which energy is emitted per square meter of surface area on the black body. And it's related to the fourth power of their temperature. And sigma here represents the Stefan-Boltzmann constant. So when we examine this as a model, as we get going to build a model here, this might be an interesting and fun game to have your students play. And if you have yourself thought of these questions, you may want to pause the video to give yourself a moment to think about them. So the game we're going to start to play is we'll imagine first two black bodies, one spherical, one disc-shaped. They have the same radius. They're presented to the same incoming beam of radiation, which will eventually take to be the incoming starlight or solar radiation. But for the moment, imagine each of these objects is in thermal equilibrium. How can we compare the radiative intensities of these two black bodies once they have achieved equilibrium? And then what will that do to help us infer their temperatures? What can we infer about the temperatures of these two black bodies? So to begin puzzling this out, first, knowing that they are in equilibrium means they must be absorbing and re-emitting or radiating energy at the same rate. And since these are objects that are presenting the same cross-sectional area to this incoming beam, each has a cross-sectional area of pi r squared, they must be absorbing energy and also radiating energy at the same rates as one another. Thing is, with the sphere and the disk, they're not going to be radiating at the same intensity as each other because the sphere can radiate over 4 pi r squared worth of its surface area. And the disk can only radiate over 2 pi r squared worth of surface area. So that gives different proportional relationships between their own radiative intensities and the incoming intensity of the solar radiation coming toward them, with the disk having a higher radiative intensity, different by a factor of 2. So that means the disk has to have the higher temperature. So working through those questions helps students then think about how we can go about calculating an average temperature for a planet, assuming again that it is a black body. Well, it's a matter of relating the incoming intensity of the incoming solar radiation to the temperature, and it's a matter of just doing this. The results that we get, because this is purely black body, the results aren't very accurate. One refining step that we can take will be to imagine, even for bodies that don't have atmospheres like our moon, they're not really good black bodies either. We can think of them as gray bodies because of the albedo that they possess. If we treat the albedo as the percent or the fraction of incident radiation that gets reflected, then we can get a better approximation of what their average temperature ought to be. For the moon, we can take this and see what we get using data that's already been collected. And basically what that means is refining our calculation previously, so that we're refining the amount of incoming radiation to be reduced by this factor of alpha. So it's 1 minus alpha is a correcting factor that we put in to figure out what an equilibrium temperature ought to be. So as I said, for the moon, we have data thanks to the lunar reconnaissance orbiter, excuse me. This is from a few years ago. The day and nighttime temperatures of the moon as measured by the orbiter, as you might suspect, it varies quite a bit due to the nature that we have a 28-day rotation period for the moon. The differences between the day and night extreme temperatures being quite vast. Nonetheless, if we calculated an equilibrium temperature from our gray body approximation, what we get is a temperature that's in the middle between the day and nighttime extremes. So That's not too shabby. For the moon, this works out okay. For other bodies, for planets, obviously the atmosphere plays a role. The particular tutorial that we have developed doesn't get into quantitative specifics with the factors that the atmosphere provides, but it allows students to think about the albedo effect will be more pronounced, obviously, with the cloud cover that an atmosphere provides, and that the greenhouse effect from carbon dioxide, water vapor, other more man-made sources of greenhouse gases. Those are going to certainly help warm the surface temperature of the planet. And in fact, it does help account for what is a 30°C or 30 Kelvin discrepancy between a gray body calculation and actual accepted average temperatures for Earth. And also, the tutorial does have a section where students will have the chance to think qualitatively about this problem known as the faint young sun paradox. An open question right now is, it's accepted that the sun in its early lifetime was 20 to 30% less luminous than it is now. Because of that, it is harder to account for the presence of liquid water on the surface of the Earth for as long as we know that it must have been here. So how to account for that? Greenhouse effect is the leading explainer to help resolve this paradox. The tutorial helps students understand the paradox itself and help students identify the greenhouse effect as indeed a reasonable candidate to help resolve this paradox. But for students who want to go further with the idea of how we go about finding the composition of exoplanets and their atmospheres, that is, we have a companion tutorial that helps students understand just that. So we invite you to look at that tutorial as well in conjunction with this particular one. So with that, I will say this tutorial on the habitable zone, we help students recognize how to build a model for accounting for surface temperatures, average temperatures of planets using basic physics ideas, and also how to refine the models that we would use with blackbody approximations and gray body approximations. And the students get to use and interact with data from NASA, in particular Kepler data. So thank you for your attention, and we hope you'll join us for future workshops where we get to share more of our results with these materials that we're making for teaching physics in astronomy and space science contexts. Thank you very much.